Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It's great to be here. This is a big one.
It really is. Today, we are exploring the history and philosophy of cognitive science. And I have to admit, as I was going through the materials for this, I had this strange, almost dizzying feeling.
Dizzying. How so?
Well, think about it. We are using our minds to think about what a mind is. We're using the very tool we're trying to investigate.
Right.
It feels like trying to see your own eyeball without a mirror. You're stuck in this loop.
That is the perfect way to put it. It's often called the ultimate recursive problem. The instrument of measurement is the very thing being measured.
And it feels like the stakes couldn't be higher. This isn't just, some abstract scientific puzzle. We're talking about the I, the self, the thing that's listening to this right now, the thing that experiences joy or dread or just decides it wants a sandwich.
It's the core of our humanity. And that brings us to the fundamental mystery, the central question we're going to keep coming back to today.
Which is?
How do you get from the physical to the mental? How does a 3-pound lump of, frankly, wet gray tissue sitting inside your skull?
Just this biological meat.
Exactly. How does that produce the entire universe of your inner world? The smell of rain, the memory of your 5th birthday, the concept of democracy.
If you were to open up a brain, you wouldn't find democracy in there. You'd find neurons and glial cells and blood vessels. You wouldn't find the color red.
Not a trace of it. You'd find electrochemical signals. That gap between the gray stuff and the technicolor experience of being alive, that's the whole game.
And while we call the field cognitive science now, and that's a relatively new label from the 1970s?
Officially, yes. But the quest itself is ancient. We've been wrestling with this since people first started thinking about thinking.
So today, we're going to trace that journey. We're going to see how the pendulum of thought has swung back and forth, sometimes in really extreme ways.
It's absolutely a pendulum. We swing from ideas where the mind is this magical preloaded thing all the way over to ideas where the mind basically doesn't exist at all.
Wait, hold on. How can you have a science of the mind where the mind doesn't exist? That sounds like a contradiction.
Oh, it happened. We'll get to it. There was a long period in the 20th century where if you even use the word thought or consciousness in a psychology paper, you were considered unscientific, a mystic.
That's incredible. Okay, so we have our path laid out. We're starting in ancient Greece with the philosophers. Then we're moving through what some people call the dark ages of this exploration. That's behaviorism.
Right, the time of the black box.
And then into the light with the cognitive revolution in the 1950s, which really sets the stage for everything happening now with AI and modern neuroscience.
And we'll end by looking at where we are today, debating whether the mind is one giant all-purpose computer or something more like a Swiss Army knife.
There is so much to get through. So let's start at the beginning. Before there were labs and brain scanners, there was just pure argument, pure philosophy. And it seems like right from the get-go, two main teams formed.
That's right, the great divide. You have the rationalists on one side and the empiricists on the other. And this argument, this tension between them, it basically defines the next 2,000 years of thought about the mind.
And the core of their disagreement was about what? Factory settings.
Factory settings is a great way to think about it. The question is, what comes built in? When a baby is born, is its mind an empty hard drive waiting for downloads, or does it come with some pre-installed software?
Okay, so let's take the first team, the rationalists. This is the pre-installed software camp.
Correct. The rationalist position is that true knowledge isn't just cobbled together from our messy, unreliable senses. Some fundamental truths are innate. They're part of our rational nature. And the origin of this idea really is Plato.
Plato and his famous theory of forms.
Exactly. Plato looked around at the physical world and saw that it was imperfect. You see a tree, but it's not a perfect tree. You see a circle drawn in the sand, but it's wobbly. It's not a geometrically perfect circle.
Right. You never encounter a perfect circle in nature.
And yet, every single one of us has the concept of a perfect circle in our mind. We can reason about it. We can do geometry with it. So Plato's question was, where did that perfect idea come from?
If we never saw it.
It must have already been inside us. He argued that these perfect forms, the form of a circle, the form of justice, the form of goodness, exist in a higher non-physical realm. And our souls, before we were born, knew them. So learning isn't about discovering new things. It's about remembering, recollecting what the soul already knows.
The mind comes preloaded. That's a powerful idea. But the rationalist who really throws down the gauntlet for the modern era is René Descartes in the 17th century.
Descartes is absolutely pivotal. He's living in this new age of science, of mechanism, and he sets himself this incredible task to doubt everything he can possibly doubt and see what's left.
And what's left is the famous cogito ergo sum. I think, therefore I am. The one thing he can't doubt is that he is doubting.
Right. But for our story, the most important move he makes is to split the universe in two.
The mind-body process.
Substance dualism. He looked at the physical world, including the human body, and saw a complex machine. You have to remember, this was a time of amazing new clockwork and automata. They were building statues that moved, powered by water.
So he sees the heart as a pump, the nerves as tubes, the muscles as levers.
Exactly. He called all of this extended substance. It's the stuff that takes up space. It's physical, it's mechanical, it follows the laws of physics.
The hardware.
The hardware. But then he looked inward at his own thoughts, his beliefs, his feelings. And he just couldn't see how that stuff, the thinking, could be part of the machine. Where's the gear for doubt? What is the lever for hope?
It doesn't take up space.
It doesn't. So he concluded it must be made of a totally different kind of stuff, a non-physical substance. Res cogitans, thinking substance.
So you have the body, which is the machine, and the mind, which is, what, a ghost driving the machine.
That's the popular caricature, and it's not entirely unfair. He created this fundamental split. And this move, this dualism, had huge consequences. On the one hand, it freed up scientists to study the body as a purely physical system without getting in trouble with the church.
Because the soul was safely on the other side of the fence.
Precisely. But on the other hand, it created this massive, seemingly unsolvable problem. If the mind is non-physical and the body is physical, how do they interact? How does my non-physical desire for coffee cause my physical arm to move?
The ghost has to pull some levers somewhere.
And Descartes never found a convincing answer. He sort of vaguely pointed to the pineal gland in the brain as the point of contact, but nobody bought it. Still, that basic division he made, the thinking stuff versus the mechanical stuff, the software versus the hardware, that metaphor has haunted us for centuries. It's the direct ancestor of the computer model of the mind.
Okay, so that's team rationalist. Team innate. The mind has built-in structures. Now let's go to the other side of the ring. Team empiricist.
Team empiricist, or team experience. They look at the rationalist picture and say, nope, all that stuff about innate ideas and preloaded software, we don't need it.
For them, the hard drive starts completely empty.
Exactly. The most famous proponent of this is the English philosopher John Locke, and he gave us the metaphor that has defined empiricism ever since.
The tabula rasa.
The white paper, or blank slate. Locke said, let's suppose the mind to be, as we say, white paper, void of all characters, without any ideas. How does it get furnished? And his answer was one word: experience.
Everything comes from the senses. There's nothing in the intellect that wasn't first in the senses.
That's the motto. You aren't born with the idea of red, you have to see red. You aren't born with the idea of sweet, you have to taste sweet. All knowledge is built up from these simple sensory inputs.
I have to say, this view always felt more, I don't know, democratic or something. We all start from the same place.
It's very appealing, but it immediately runs into a huge problem. And it's the one you hinted at earlier.
The organization problem.
Yes. If the mind is just a passive bucket, and you're just pouring in experiences, a flash of red here, a sound of a bark there, a feeling of warmth, how does it get organized?
Right. How does the mind know to bundle bark, fur, forelegs, and wagging tail together into the concept of dog? If it has no built-in rules, it should just be a chaotic soup of sensations.
A total mess. The empiricists needed a mechanism. If the mind isn't actively structuring things, what is?
So what was their answer?
Their answer was a single powerful principle: association.
Mental glue.
That's the perfect term for it. The idea is simple. Things that are experienced together become linked together in the mind. The Scottish philosopher David Hume tried to turn this into a science. He wanted to be the Isaac Newton of the mind.
So Newton has laws of physical gravitation.
And Hume proposed laws of mental association. He said ideas get linked together through a few basic principles. First, resemblance. An idea of a face makes you think of the actual person. Second, contiguity in time and space. If you always see lightning and then a second later hear thunder, your mind glues those two ideas together.
Because they happen close together.
And third, cause and effect. The idea of a wound makes you think of the pain that follows. Hume believed that the entire complex tapestry of human thought could be woven from these simple associative threads.
And Later empiricists, like James Mill and his son John Stuart Mill, they took this even further, right?
Yeah.
They talked about mental chemistry.
They did. This is a fascinating idea. They argued that simple ideas combine to form complex ideas, but not just by being added together, like bricks in a wall. They thought it was more like how chemical elements combine to form a new compound.
So hydrogen and oxygen are both gases, but you put them together and you get water, which is something completely different.
Exactly. They said simple sensations like red, round, and sweet could chemically fuse in the mind to create the entirely new, complex idea of apple. The whole is different from the sum of its parts. But, and this is the key, it's still a passive process. The mind isn't deciding to do this. The associations are just happening, like chemical reactions.
And we have to put a big red pin in this idea of associationism, because this is basically the blueprint for how a lot of modern AI works, isn't it?
It is the direct ancestor. When you hear about neural networks and deep learning today, what are they doing? They are statistical association machines. They are fed massive amounts of data, pictures, text, and they learn to associate patterns. These pixels usually go with the word cat. It's Hume's contiguity principle on steroids.
But the empiricist dream is alive and well in Silicon Valley.
It's had a major comeback.
Okay, so for centuries, we have this heavyweight fight. Team rationalist with their innate structures versus team empiricist with their blank slate and associations, and it feels like a stalemate. And then, in the late 18th century, a German philosopher walks into the room and says, "You're both wrong, and you're both right."
And that philosopher is Immanuel Kant.
Yeah.
And he completely changes the terms of the debate. Kant is famously difficult to read, but his central idea is a game changer.
So how can we break it down?
Kant starts by acknowledging that the empiricists have a point. He says, no doubt, all our knowledge begins with experience. He's not a pure rationalist.
Okay, so he agrees we're not born knowing what a dog is.
Right. But then he says, but though it begins with experience, it does not all arise out of experience. He saw that neither side could explain the whole picture, so he came up with what he called his Copernican revolution in philosophy.
Just like Copernicus showed, the Earth revolves around the sun, not the other way around.
Kant did the same for the mind. He said, up until now, we've assumed that our minds must conform to the world. We're just passively receiving information. But he says, what if we flip it? What if the world must conform to our minds?
Whoa. Okay, unpack that. That sounds radical.
He used a method he called the transcendental method. Instead of just looking at what's in the mind, he asked a deeper question. What must the mind be like in the first place for us to have any experience at all?
He's reverse engineering the conditions of possibility.
Exactly. Think of it like this. Imagine you were born wearing a pair of blue-tinted glasses that are permanently fused to your face. You can never take them off.
Okay. Everything I see looks blue.
Right. Now, a strict empiricist would look at your experience and say, the world is blue because all the data coming in is blue.
But that's wrong.
It is. The blueness isn't a property of the world. It's a property of the instrument you're using to see the world. Kant said our minds have these built-in glasses. These are innate structures.
So he's siding with the rationalists.
Not quite. Because these structures are empty, they're like a filing system without any files in it. Or a better analogy might be a cookie factory.
The cookie factory. I like that.
Kant said the world provides the raw, formless dough of sensation. That's the empiricist part. But our mind is the factory. It has all these machines and cookie cutters that actively shape that dough into the cookies of our experience.
So the cookie cutters are the innate structures.
Yes. He called them the forms of intuition and the categories of understanding. The two most basic cookie cutters are space and time. Kant's radical claim was that space and time are not features of the external world. They are the fundamental coordinate system of our mind. We can't experience anything except through the lens of space and time.
So my mind stamps everything with a location and a timestamp.
It has to. And it also stamps experience with other categories, like causality, the idea that one thing causes another. Hume thought we just learned that from habit. Kant said no, causality is a rule of the mind. The mind is programmed to look for causes and effects. It's how it makes sense of the raw data.
So we don't just passively receive reality. We actively construct it. We are the architects of our own experience.
That's the Kantian synthesis. The mind is not a blank slate, but it's also not full of preformed ideas. It's an active engine that imposes structure on the sensory chaos from the outside world.
That's a huge shift. But here's the kicker. Even though Kant basically invented the modern framework for the mind, he was deeply skeptical that psychology could ever be a real science.
He was. And it's a fascinating paradox. He laid the philosophical groundwork and then immediately said, don't even try it.
Why? What was his reasoning?
Well, for Kant, a true science, like physics, had to be grounded in mathematics. You had to be able to apply numbers and measurement to things. And crucially, those things had to exist in space.
You can measure the trajectory of a cannonball through space.
Exactly. But what about a thought or a feeling of sadness? He argued that mental events exist only in time, not in space. You can't put a ruler to a memory. You can't put a thought on a scale and weigh it.
It have no physical dimensions.
Right. And therefore, he concluded, you can't apply mathematics to it, so it can never be a proper natural science. He also pointed out another problem: introspection. The act of observing your own mind changes what you're observing.
The observer effect. If I try to carefully analyze my feeling of anger, the act of analyzing it cools it down and changes the feeling itself.
Precisely. You can't get a clean measurement. So since studying the mind from the inside was unreliable, Kant suggested the only way forward was a kind of anthropology, studying human beings from the outside, observing their behavior in society.
Which is an incredible piece of foreshadowing for what happens next.
A huge one. He basically predicted the rise of behaviorism over a century before it happened.
So despite Kant's warning, in the 19th century, people start trying anyway. We get people like Wilhelm Wundt in Germany setting up the first psychology lab in 1879.
Wundt and others, like William James in America, were the pioneers. They were trying to make psychology a respectable science, but they were still relying heavily on that method Kant warned about, introspection. They'd train people to be observers of their own minds.
So they'd, what, flash a light and ask someone to describe their inner sensations in minute detail?
Yes. I perceive a greenness of a certain hue, followed by a feeling of mild surprise. It was painstaking, but it was also incredibly subjective and unreliable. My mild surprise is your shock. How can you build a science on that?
You can't. And that leads to a backlash, a massive overcorrection in the early 20th century.
The pendulum swings all the way to the other side. This is the rise of behaviorism.
And the key figures here are John B. Watson and later the even more influential B.F. Skinner.
And their basic message was a complete rejection of everything that came before. They looked at introspection and said, this is a joke. This isn't science. It's glorified philosophy.
They wanted psychology to be like physics, hard, objective, measurable.
Exactly. And what can you measure? You can't measure a thought. You can't see a belief. But you can see and measure behavior. So they made a radical proposal. Psychology should be the science of behavior and nothing else.
They threw the mind out completely.
They called it the black box. You have an input from the environment, a stimulus, and you have an output from the organism, a response. What happens inside the box, the mind, is irrelevant and unscientific. You don't need to talk about it.
So for a behaviorist, if I see a bear in the woods and I run, you don't need to say I felt fear or believed I was in danger.
Nope. You just say, the stimulus of the bear produced the response of running. That's all the science needs. Skinner argued that all human and animal behavior, no matter how complex, could be explained by a history of reinforcement.
You do something, and if you get a reward, you're more likely to do it again. If you get punished, you're less likely.
That's the whole system. He even wrote a book arguing that language is just learned this way. A baby babbles, happens to say mama, the mother gets excited and gives the baby a hug, and the sound is reinforced. No need for any complex mental grammar.
This philosophy dominated American psychology for decades. It was the only acceptable way to do things. But it couldn't last. Cracks started to appear in the walls.
They did. And funnily enough, some of the biggest cracks came from within their own labs, from experiments with rats. Which brings us to a hero of cognitive science, Edward Tolman.
Tolman and his cognitive maps. I love this story.
It's a fantastic story. So Tolman was, on the surface, a behaviorist. He ran rats through mazes, which was the classic behaviorist experiment.
According to strict behaviorism, what is the rat learning when it runs the maze?
It's learning a simple chain of stimulus-response behaviors. At this junction, turn right. At the next one, turn left. It's just muscle memory, a mindless automaton.
But Tolman suspected something more was going on.
He did. So he ran a clever experiment. First, he let a group of rats just wander around a maze without any food reward. According to behaviorism, no reward means no learning should happen.
Right.
Then he put food at the end and timed them. And he found that these rats, the ones who had just explored, learned the maze almost instantly, far faster than rats who had never seen it before.
So they were learning something on their wanderings, even without a reward.
They were building a map in their heads. But the killer experiment was when he trained a rat to find food down a specific path. Then he blocked that path.
If the rat is just a stimulus response machine, it should be stuck. It should keep trying the turn right command that's now blocked.
Exactly. But that's not what the rats did. They would go to the blockade, pause, and then almost immediately take a new, different path that was the most efficient shortcut to where the food was.
To do that, they couldn't just know a sequence of turns. They had to know the overall layout of the maze.
They had a mental representation, an internal picture. Tolman called it a cognitive map. And that phrase, cognitive map, was dynamite. Because a map is not a behavior, it's an information structure. It's something inside the black box.
The rats were thinking.
The rats were thinking. And if rats were building cognitive maps, it was a pretty safe bet that humans were doing something a lot more complex than just responding to stimuli. The behaviorist dam was starting to break.
So the pressure is building throughout the 40s and 50s. And then we come to a specific date, which is often called the birthday of the cognitive revolution.
September 11th, 1956, a symposium on information theory held at MIT.
It's so rare in the history of ideas to have such a precise starting point. What happened on that day?
It was this incredible moment of convergence. You had brilliant people from 3 completely different fields who had all been working on the failure of behaviorism from their own angles. And on that day, they all presented their work and realized they were all part of the same new movement.
So who are the founding fathers at this meeting?
First, you have the psychologist George Miller. He presented what became one of the most famous papers in psychology history, the magical number 7, plus or minus 2.
This is the idea that our short-term memory can only hold about 7 things at a time, like the digits in a phone number.
Right. But the revolutionary part wasn't the number itself. It was the way he thought about it. He treated the mind as an information processing channel, like a telephone wire. He said the mind has a limited channel capacity. He was applying concepts from engineering and computer science to the mind.
He was quantifying a mental process. He was measuring the bandwidth of the mind.
Precisely. This was a direct attack on the idea that you can't measure what's in the black box. Miller showed that you can.
So that's psychology making a comeback. Who was next?
Next was the linguist, a young, fiery Noam Chomsky. He was there to basically demolish Skinner's behaviorist theory of language.
The idea that we just learn by reinforcement.
Chomsky argued that this was mathematically and logically impossible. He pointed out that language has a quality called productivity. We can produce and understand an infinite number of sentences we've never heard before.
Like his famous example. Colorless green ideas sleep furiously.
That's it. It's a grammatically perfect sentence that has never been uttered before and makes no sense. A simple reinforcement model can't explain how we can generate or understand it. Chomsky argued that we must be born with an innate, built-in universal grammar, a set of rules for language processing.
He was bringing back Kant's innate structures, but for language.
He was. It was a rationalist revival. He put the mind back into the study of language.
And who was the third pillar of this revolution?
The computer scientists Alan Newell and Herbert Simon. And they came with a demonstration. They showed off a program they had created called the Logic Theorist.
And what did it do?
It proved theorems in mathematical logic. It was arguably the first artificial intelligence program. It was doing something that, up to that point, was considered a hallmark of human reason.
A machine was thinking.
And that was the final, crucial piece of the puzzle. Miller showed you could measure mental processes. Chomsky showed that the mind must have complex internal rules. And Newell and Simon showed that a physical machine, a computer, could manipulate symbols according to rules to produce intelligent behavior.
And when you put those 3 things together,
You get the cognitive revolution, and you get its central guiding metaphor, the computational theory of mind, the idea that thinking is a form of computation.
the mind is the software, the brain is the hardware.
That became the dominant paradigm for the next 50 years. It solved Descartes' problem without needing a ghost. The mind isn't a spooky, non-physical thing. It's the program that the brain is running.
And this leads to an idea called functionalism.
Yes, functionalism is the idea that what matters for having a mind is not what you're made of, but what you do. It doesn't matter if your brain is made of neurons or silicon chips or, tinker toys. If it can run the right program, if it can implement the right functions, then it has a mind.
So thinking is defined as information processing. It's the manipulation of internal symbols or representations according to a set of rules or algorithms.
Exactly. And this brings up a really important distinction: syntax versus semantics.
Rules versus meaning.
Right. A computer operates purely on syntax. It shuffles symbols around based on their shape and the rules in its program. It doesn't know what the symbols mean. The big bet of the early cognitive scientists was that if you could just get the syntax right, if you could figure out the rules of the brain's program, then the semantics, the meaning, would somehow take care of itself.
That feels like a very big bet.
It was a huge bet, and one we're still debating today.
So once this new computer metaphor takes hold, the next obvious question is, what kind of computer is the mind? Is it one big general-purpose PC that can learn to do anything?
Or is it more like a smartphone with a bunch of specialized pre-installed apps for doing specific jobs?
And that question brings us to another giant in the field, the philosopher Jerry Fodor.
Fodor is essential. In the 1970s, he argued for something he called the language of thought, the idea that we think in a kind of internal, unspoken language he called mentalese. But his most influential work came in 1983 with a slim but powerful book called The Modularity of Mind.
And he argued for the app model, the Swiss Army knife.
Yes. Fodor looked at the evidence and argued that the mind is not one single unified computer. Instead, he proposed that large parts of it are modular.
Meaning it's made up of specialized little machines.
Mental organs. He argued that, just like the body has a heart for pumping blood and lungs for breathing, the mind has dedicated modules for specific tasks. A face recognition module, a language processing module, a module for perceiving 3D space.
And he had a very specific checklist for what counted as a module, right? They had to have certain properties.
That's right. First, modules are domain-specific. They are highly specialized. Your language module only processes language. It doesn't help you do calculus. Your face recognition module only does faces. It doesn't recognize cars.
Okay, that makes sense. What's next?
Second, modules are fast and mandatory. You don't have to think about using them. They just turn on automatically. When someone speaks to you in a language you know, you can't not hear it as words. It's a reflex. You can't decide to hear it as pure sound.
And when I open my eyes, I can't help but see a world of objects and surfaces. It just happens.
Instantly. But the third and most important characteristic of a module for Fodor was that they are informationally encapsulated.
Encapsulated, like a sealed capsule.
Exactly. It means the module is sealed off from the rest of your mind. It does its job without access to your general knowledge or beliefs. It's a dumb, dedicated reflex.
And the best way to understand this is with an optical illusion.
The classic proof. Take the Muller-Lyer illusion. You have two horizontal lines. One has arrowheads pointing in at the ends. The other has arrowheads pointing out.
And the one with the arrowheads pointing out looks longer.
It looks significantly longer. But you can take a ruler and measure them, and they are exactly the same length. Now, here's the crucial part. Even after you've measured them, even after you know for an absolute fact that they are the same length,
it still looks longer. I can't make myself see them as equal.
You cannot. Your central conscious belief system, the lines are equal, cannot penetrate and influence the operation of your visual module. The visual module is encapsulated. It follows its own built-in rules for interpreting 2D lines as 3D depth cues, and it doesn't care what you think you know.
That's a powerful demonstration. It feels like my mind is arguing with itself.
It is. It shows that the mind isn't a unified whole. It's a collection of systems, and some of them don't talk to each other.
But Fodor didn't think the whole mind was modular, did he?
No, and this is where his theory gets really interesting and a bit pessimistic. He said, sure, our input systems, vision, hearing, language, are modular. They're the fast, dumb reflexes that feed data into the system. But what about the central part of the mind, the part that does the actual thinking?
The part that takes the output from the vision module and the language module and decides, I should probably sell that stock, or I think she likes me.
Exactly. Belief formation, problem solving. He called these the central systems, and he argued that they are the complete opposite of modular.
How so?
He said they are isotropic and Quinian, which are just fancy words for saying that in central thinking, anything can be relevant to anything else. When you're trying to solve a hard problem, you might need to draw on a memory from your childhood, a fact from a book you read last year, a feeling you have in your gut.
Everything is connected to everything.
It's a holistic free-for-all. And because of that, Fodor was deeply pessimistic that we could ever have a true science of higher order thinking. He basically said, we can understand the mind's reflexes, but we'll never understand the mind's creativity or wisdom. He called it Fodor's first law of the non-existence of cognitive science.
Wow. So the founder of modularity theory basically said his own field had a built-in dead end. That's a bit of a buzzkill.
It is. But it highlights the immense difficulty of the problem. And this difficulty, this gap between simple rule following and genuine holistic understanding sets the stage for the single biggest challenge to the entire mind as computer project.
We have to talk about the Chinese room.
We have to talk about John Searle's Chinese room. This is probably the most famous thought experiment in the philosophy of mind from the last 50 years.
And its target is strong AI, right? The idea that a sufficiently complex computer program doesn't just simulate a mind, it actually has a mind it understands.
That's the target. Searle wanted to blow that idea out of the water, so he asks us to imagine the following scenario.
Okay, walk us through it.
Imagine me. I am locked in a room, and I do not speak or understand a single word of Chinese.
Okay, you're in the room. No Chinese.
Inside the room with me are several big baskets filled with Chinese symbols, just squiggles and lines to me. And I have a giant rule book written in English.
What does the rule book say?
It's a set of purely formal syntactic rules. It says things like, if you see a symbol that looks like a squiggle, find the symbol that looks like a squoggle in the other basket and pass it out. It's just matching shapes.
You don't know what any of it means.
Not a clue. Now, outside the room, there are native Chinese speakers. They are passing questions written in Chinese into the room through a little slot.
Don't know their questions, they're just more squiggles.
Exactly. I take the input squiggles, I look up the rule in my English book, I find the corresponding output squiggles, and I pass them back out through the slot. Now, let's say this rulebook is so good, it's the perfect AI program, that the answers I'm passing out are completely indistinguishable from those of a native Chinese speaker.
So to the people outside, it looks like the room understands Chinese perfectly. They ask, what is your favorite food? And the room answers, Peking duck.
Perfect answers. Every time. Now, here is Searle's killer question. Does anyone or anything in this scenario actually understand Chinese?
Well, you, the person in the room, certainly don't.
Not a single word. I'm just manipulating uninterpreted symbols. I have the syntax down perfectly, but I have zero semantics, zero meaning.
And Searle's point is that the digital computer is just you in the room. It's a symbol shuffler.
Wrong.
It's running the program, but there's no understanding going on.
That's the conclusion. Syntax is not sufficient for semantics. No matter how complex the program, it can never, by itself, give rise to genuine meaning or consciousness. It's a simulation, not a duplication.
Okay, but there are famous replies to this. I have to play devil's advocate. The most common one is the systems reply.
Let's hear it.
The systems reply says, okay, fine. The person in the room doesn't understand Chinese, but you're looking in the wrong place. The entire system, the person, plus the rule book, plus the baskets of symbols, plus the room itself, that whole system understands Chinese.
A very clever reply, but Searle has a rebuttal.
What is it?
He says, okay, let's internalize the system. Imagine I get rid of the baskets and the book, and I memorize all the rules, and I do all the symbol shuffling in my head. Now I am the entire system. There's nothing outside of me. I receive the Chinese symbols, run the program in my imagination, and produce the output.
Okay.
Do I understand Chinese now?
No. You're still just running the rules. You still don't know what the symbols mean.
Exactly. The understanding is still missing.
What about the robot reply? They say the problem is the room is disconnected from the world. If you put the computer program inside a robot with cameras and arms, so it can see and interact with things.
So it can see a bowl of noodles and associate the symbol for noodles with the actual thing?
Right. Then the symbols become grounded in reality. They gain meaning.
Searle thought that didn't solve the problem either. He said all you've done is add more inputs and outputs. Now you have a stream of data from a camera, but inside the robot's CPU, it's still just the guy in the room manipulating symbols according to a rule book. The fundamental problem of where the meaning comes from hasn't been touched.
It's a really stubborn argument. It seems to put a hard limit on what pure computation can achieve.
It does. And it pushes the science in new directions. If the simple computer metaphor isn't enough, what comes next? And that brings us to where cognitive science is today. We're seeing a move away from the brain as digital computer model and towards something more biological, more integrated.
And one of the biggest ideas right now is something called predictive processing, or the predictive brain.
This is a huge shift, and fascinatingly, it's almost like we're coming full circle back to Kant.
How so?
The classic view of perception, the one that fits the old computer model, is bottom-up. Information comes in from the senses, and it's slowly built up into a picture of the world, step by step.
But the predictive processing model flips that on its head.
It says the brain operates primarily top-down. The brain is not a passive receiver of information. It is an active, constantly running prediction machine.
So as I'm sitting here, my brain isn't just taking in the light from the microphone. It's constantly predicting what the microphone should look like, sound like, feel like.
Yes. Your brain is generating a hypothesis, a model of the world. And it uses sensory input not to build the model, but to check the model. The only information that flows up from the senses is prediction error.
The surprises, the
Yeah.
things that don't match the prediction.
Exactly. If the microphone suddenly turned to a banana, you'd get a huge prediction error signal, and your brain would frantically try to update its model. But as long as the world behaves as predicted, the brain is happy. This is a direct echo of Kant's idea that the mind imposes its structure on the world.
So in a sense, perception isn't the process of letting the world in. It's the process of our brain's best guess meeting reality.
So some neuroscientists even describe it as a controlled hallucination. We're all constantly hallucinating our reality, and it's just kept in check by sensory data.
That is a mind-bending idea. And this top-down, model-building view is also changing how we think about social cognition, isn't it? How we understand other people.
It is. The old view of theory of mind was that we have a little module for figuring out what others are thinking. The new view is that we are constantly running simulations or models of other people's minds. We use our own mind as a template to predict what you will do or think.
I predict what you will do based on my model of what you believe and what you want.
It's deeply recursive and computationally intensive, which is why social life is so complicated and exhausting.
Tell me about it. And finally, there's this other big movement trying to break out of the brain in a vat model, the 4E cognition school of thought.
Right. This is another reaction against the pure computational model. 4E stands for embodied, embedded, enacted, and extended.
Okay, break those down for us.
Embodied means that thinking is fundamentally shaped by the fact that we have a body with particular abilities and limitations. Our concepts are grounded in physical experience. Embedded means cognition doesn't happen in a vacuum. It happens in a rich, real-world environment that we rely on.
And what about the last two?
Enacted means that we enact our world. We don't just represent it. We think through acting. And extended is the most radical one. It's the idea that the mind doesn't stop at the skull.
The mind leaks out into the world.
Yes. Think about when you use a notebook to solve a math problem, or when you use the calendar on your phone to remember appointments. The 4E argument is that that notebook or that phone is not just a tool for your mind. For that moment, it is literally part of your cognitive system. Your memory circuit extends to include the phone.
So my mind isn't just the software in my head. It's a dynamic system that includes my brain, my body, and the tools I use in my environment.
It's a far more holistic and integrated view than the old brain as a computer idea.
So looking back on this whole incredible journey, we've gone from Plato's perfect forms to Descartes' ghost in a machine, from Locke's blank slate to Kant's mind factory, then through the barren desert of behaviorism and into the promised land of the cognitive revolution with its computer metaphor.
And then we saw that metaphor challenged by Fodor's modules and Searle's Chinese room, pushing us toward these newer, more integrated models like the predictive brain and 4E cognition.
It seems like the central tension, the one that started it all, is still right here with us.
It absolutely is. It's the tension between the rule-based, syntactic, computational view of the mind
and the messy, meaningful, semantic, conscious experience of being a human.
The computer model is fantastic at explaining the logical, rule-governed parts of our intelligence, but it still struggles to explain the what it's like part, the qualia, the meaning.
And maybe that's the fundamental question we're left with. Are we computational machines that have somehow evolved the illusion of meaning?
Or are we meaningful beings who happen to use computation as one of our tools? The debate is far from over.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.